Hi, my name is Harrison Gettner and I'm the team lead for Team 21060, Laser Diode-Based Metrology Module, sponsored by ASML, Paul McKenzie, Eric Berta, and mentored by Don McDonald. And here with me are my team members.
唱歌
Nathan Jocelyn,
Amarjeet Pandey,
Luis Solorio,
Joseph Zuha.
ASML is a manufacturer of photolithography equipment for the semiconductor industry. The current metrology solution employed by ASML to precisely locate tin droplets in the light source of their machines is bulky and difficult to service, which reduces uptime and overall wafer output when in need of repair. Our team investigated a proof of concept prototype module, which is both compact and easy to service, which will serve as a stepping stone for ASML to refine their metrology systems. Our system, the Laser Diode-Based Metrology Module, LDMM, creates a stream of sub-millimeter water droplets and then detects the position of these droplets using a laser diode-based optical metrology system. A fast solid-state detector is employed to detect the reflection of visible laser light from the surface of the droplet. Once the system detects a droplet, it sends a timing signal to an external LED that signifies the detection has been made. The team also developed an application that provides a graphical interface and allows the user to operate the LDMM through a host computer. ASML's requirements for this prototype included the ability to produce droplets which are smaller than 1 millimeter in diameter and at a frequency of at least 1 droplet per second. In order to ensure compactness and serviceability, the system was limited to a size of no greater than 2 feet on each side and a total weight of 20 kilograms. The system needs to be able to record droplets with 99% accuracy using a laser diode with less than 5 milliwatts of optical power for safety. With such stringent requirements, our team investigated the best possible solutions that could meet and exceed the standards put forward by ASML while also maintaining our budget.
We designed the LDMM to be equipped with a Droplet on-demand piezoelectric droplet generator. After much analysis, a custom-built droplet generator proved to be the most cost-effective solution while providing the highest control for droplet size and frequency. For illumination and detection, we implemented an optical metrology design that consists of a 650 nanometer laser diode and a solid-state silicon photodiode detector. Our choice of detector came from our need for an inexpensive detector with a fast rise time capable of rapid detections. An Arduino microcontroller operates the major functions of the system and runs data acquisition. The Arduino accepts input from a GUI on the computer and controls the piezoelectric droplet generator. The Arduino also collects data from the photodiode and displays it on the GUI. The GUI was developed in the C# programming language as a Windows Form application. The LDMM is assembled on top of an optical breadboard, equipped with vibration isolators, and is enclosed with black panels to minimize light interference. The design choices investigated by the team offer a solution that meets the requirements set forth by ASML in an accurate and cost-effective manner.
The droplet generation system uses a 35mm piezoelectric disc operated by a 40-volt DC power supply and Arduino working in unison to create droplets on demand. It is composed of an aluminum extrusion frame, custom machined water reservoir, droplet chamber, and chamber lid, as well as 0.6mm brass nozzle. Plastic tubing carries the water from the reservoir to the chamber, and drops are caught by a 3D printed droplet catcher designed with splash mitigation in mind to prevent any water from degrading the performance of the optical components. The sudden application of positive 40 volts to the piezo causes it to flex, generating a positive pressure pulse in the chamber and dispensing a droplet. Inverting the voltage causes the piezoelectric to contract, drawing liquid from the reservoir back into the chamber. This repeating sequence is what allows the subsystem to expel droplets on demand. The optical metrology subsystem is split into illumination and detection subassemblies. The illumination subassembly uses a 655 milliwatt laser diode as the illumination source and a 100mm plano-convex lens to collimate the diverging light from the diode onto the droplets. The illumination subassembly is housed by a 3D printed barrel, which is affixed to a 3D printed angular adjustment plate. The adjustment plate is mounted to an aluminum extrusion base, allowing us to fine-tune the height and angle of the incident light, maximizing the light reflected off the surface of the droplet. Here we set the angle of incidence to be roughly 60 degrees, resulting in 10% optical power from the droplet surface. The detection subassembly is composed of a 25mm plano-convex lens and FDS 1010 large area silicon photodiode. The detector has a 65 nanosecond rise time, strong current responsivity in the visible range, and its large square centimeter area reduces the tolerancing requirement of the mechanical alignment. The components sit in a custom 3D printed housing where the detector rests at an angle of 60 degrees. This predetermined angle matches the illumination subassembly, maximizing the amount of reflected light being captured. A demonstration of the system working with our observation window open can be seen. We are able to visualize how each subassembly works in unison to create, illuminate, and detect droplets at varying frequency. In this test, we can visualize the system generating a constant stream of droplets, as well as hear the piezoelectric disc contracting and expanding at a frequency of 1 Hz.
So here we have a demonstration of the laser diode metrology modules. We have the following settings for our GUI, which are frequency in hertz for the droplets to be generated, number of droplets to be generated, the LED settings, which we will turn on as on because this is the LED that blinks in green whenever we have a droplet which is detected. We also have a COM port settings, which we will use to connect the computer to the Arduino using the USB port. And so we can use run the following settings in the droplet settings, which we enter here. We can use prep nozzle, which comes predetermined with 1 Hz and continuous generation of droplets. We have emergency stop, and we have an export option which will export all the data being generated here. So for the sake of this demonstration, I will go with 1 Hz and 15 droplets. As we can see here, data is fluctuating between a low point of 0 and somewhere along 25 or 30. 30 is when a droplet is being detected, and 0 is when there is no droplet being detected. And we can see the green light here also is flashing every time a droplet is detected. So in our case, we had created 15 droplets, and 15 droplets were detected.
In terms of the system performance, we have conducted 3 acceptance tests. Being able to control and estimate the droplet size is very crucial for our project. So we designed a testing method to accurately measure the size of the droplet for a given nozzle. With a 0.6 mm nozzle, here is a picture of the generated droplets. From the nozzle's outlet, there is a stream of water composed of multiple droplets, and then it gradually forms single droplets. After importing this image into the MATLAB code, the width of the aluminum extrusion is selected as a reference distance. So with the pixel to millimeter conversion, the diameter of this stream of water is 0.6 millimeter, and the single droplet is 0.8 millimeters. Then we repeat the same steps to analyze a few images and characterize the precision of this droplet generator by calculating standard deviation. Their sizes meet our requirement. For the laser power test, we shine the laser light directly on the silicon photodiode and measure the current, which was 1.68 milliamps. Based on the photodiode's responsivity, the calculated output power of the laser light was 4.2 millivolts. The droplet frequency is one of the input parameters of the GUI software. Droplets shall be generated and detected with a minimum frequency of 1 Hz. This is verified by measuring the time it takes to create a specific amount of droplets, and the frequency of droplet is simply equal to the amount of droplet divided by time. For the system accuracy test, we could go through the output data displayed in this section of the interface. The data is derived from the serial monitor and Arduino. It shows the amount of droplets generated and detected. This test verified our system accuracy is 99.65% up to 3 Hz. In other words, 99.65% of the droplets in the generated signal are registered.
In conclusion, the team developed a functional metrology system which strategically employs precision components to avoid unnecessary expense and maintain an accurate and cost-effective solution. The system could be a forerunner to similar designs optimized to detect droplets of other substances. This concludes Team 21060's presentation of the laser diode metrology module. Thank you for watching.